Hello and welcome to another edition of Portland State University's live stream for Chemistry 222. Ignore me while I fix my background a little bit. Okay. Today we're going to be talking about the change in boiling point and freezing point, a lot of the solubility rules and stuff like that. We're going to go over molality and work on what becomes soluble and what are the different stages of solubility measurements and stuff. First, I'd like to post a few links in the chat again. Through links to the Learning Center's website, our Facebook and Instagram page. Definitely check them out and follow them on Facebook. You can also, I'll post a link to the Penji app, which is where you would go if you're looking for tutoring. We have a great tutor, Amir, who's our chemistry tutor this summer, and he'd be happy to make an appointment with you and help you out with any questions you might have. Also, stick around in the Penji app just after this live stream, and I'm going to have a drop-in tutoring session. So you go into the Penji, go to the Chemistry 222, or just chemistry in general, either one, and you should find me in the drop-in room there. So if you have any questions, I'm happy to work through it. I'll be there till 5 p.m. today. Finally, if you wanted to look at any of the past videos for either Chem 221, Chem 222, or anything, check out the Learning Center's YouTube page. We put all of the videos that we have up here, all the live streams get posted on there within about 24 hours of here. So definitely check back on there as well. Let's go ahead and get started today. So this first one's talking about whether or not different molecules are soluble. And during the last week, we talked a lot about the different type of intramolecular forces there are. So, or intermolecular forces. So to recap, those are the London dispersion forces, the dipole-dipole forces, and the hydrogen bonding forces, and what type of molecules have which and stuff. So in this question here, we want to predict whether the following substance would be more soluble in water, a polar solvent, or a hydrocarbon such as heptane, which is a non-polar solvent. And they tell you here, heptane is C7H16. So a lot of that comes down to the differences of the intermolecular forces. And really, for something to be soluble, the force between the two the solute and the solvent need to be equal to or greater than the forces between itself, essentially. So I'm going to write that up here. Solute, solvent. Those forces need to be greater than or equal to the solute forces. So that's how well the solute bonds to itself. Or that same thing is going to be true for the solvent forces. And that's also the same idea. The solvent forces the forces between the two solvent molecules will bond to each other better than they bond to the other things. You're going to get something that's miscible. They're not really soluble in each other. And there's a general rule behind a lot of these that I've heard in the past, which is like dissolves in like. So the idea is if something's polar, it's going to dissolve in a polar solvent. If something's non-polar, it's going to dissolve in a non-polar solvent. That's a general rule of thumb. There's definitely degrees of polarity and stuff. There's some things that are somewhat soluble, but not really soluble, and we can definitely work on those a little bit here. But here we're looking at the three key ones: vegetable oil, isopropyl alcohol, and potassium bromide, which is an ionic compound. So starting out with the vegetable oil, I'm going to call it veggie oil. This is just the soybean oil, something that you cook with at home. It is non-polar, which is a lot of the oils are just long strings of hydrocarbons. So in this one, we want to compare it first to water and then to heptane. So for water, which is a polar solvent, we can see, I want to look at the different types of intermolecular forces here. Vegetable oil, being a long string of hydrocarbons, is essentially just going to have that dispersion force intermolecular force. It's not a polar thing, so it doesn't have the dipole-dipole, and without that OH, NH, or FH bonds, it's not going to have hydrogen bonding either. So it's going to have a fairly weak bond between them, but comparing it to water, which has that London dispersion, because everything really does. Everything has that ability to kind of redistribute the electron charge around its atoms a little bit and have that instantaneous dipole. But it also has a dipole-dipole. I'm going to say that's DD for dipole-dipole. Because water is a polar compound, which means it's, in this case, oxygen and hydrogens are down there, and it's a bent molecule. It ends up with a set of electron densities up at the top in that tetrahedral shape. So there's a top cluster which has a higher electron density than the bottom. So you end up with a partial negative up there, and you end up with more of a partial positive down there, which creates that dipole moment between everything, right? So that dipole-dipole is very strong reaction and intermolecular force for water to bond to itself compared to the veggie oil. So the water stays bonded to itself and the veggie oil can't really get mixed in there very much. So I would say that these they're not soluble with each other, and they wouldn't work well. Now if we compare that to heptane. So heptane, I'm going to draw a line structure. 1, 2, 3, 4, 5, 6, 7 carbons in a row. Each of those carbons is fully populated with hydrogens, which means the end ones have 3 hydrogens, and the secondary carbons in the middle have 2 hydrogens on each one. We can see there's no, it'll have London dispersion, but there's no real dipole here, because by filling these with hydrogens, all my pink are going to be hydrogens. We see that it's basically surrounded by these hydrogens, and there's no real polarization going on there, at least not from a dipole's perspective. So it wouldn't have dipole-dipole, and with a lack of oxygen, nitrogen, and fluorine, it's not going to have your H bonding. That's the one thing I missed in water. Water has H bonding. So in this case, heptane is going to just have that London dispersion, which is the same as oil. So we can see that the bond strength between those two is going to be about the same, and those are going to actually bond together. Maybe I should say these are approximately equivalent. Okay, you want about the same intermolecular forces going on between the solute and solvent as you have between the solvent and solvent and the solvent and, or solute and solute. So that's part A, where we say that veggie oil would bond it to heptane. They're both non-polar. That's where it gets that like bonds with like. If we look at part B is isopropyl alcohol. Which is a polar compound. And it's polar because isopropyl has 3 carbons. I got my hydrogens on there. But it also has 1 oxygen with a kind of an OH, a hydroxy function kind of attached to that center carbon. So it makes it the isopropyl. This one is going to be a polar icon or atom because of these electron densities we have around that oxygen again. It's similar to water in that way. So it's going to have not just London dispersion, but also dipole-dipole and H bonding. And the H bonding is because it has that OH group on there. So it can bond, it can provide that hydrogen, it can accept hydrogen H bonding both ways. And that's going to be the same as water, because water has all of those things. It's London dispersion, dipole-dipole, and H bonding. So like bonds with like solutes with like. And that's going to work well. But if we compare that now to how that's going to do with heptane, again, a nonpolar. And heptane just has, we said, that London dispersion bonding. The isopropyl alcohol is too happy bonding to itself. It doesn't really want to bond with the heptane. There's no dipole-dipole interaction. There's no H bonding interaction. So that's not going to happen down there. For part C, that's potassium bromide. So this is an ionic compound. So when you mix ionic compounds into water, they dissociate into their ions, most likely. So water being a polar molecule, it'll dissociate, and basically that polar molecule has that dipole moment, so it surrounds the different different ions floating around in there. So for example, if I had a potassium plus, we're going to get these water molecules floating around in here, and I should put my H's on. And notice I have the oxygen closest to the potassium. Potassium is positively charged. The oxygen has that partial negative, and it's not a full negative. I should put 2 lone pairs on each of them. 2, 3, 4. So that partial negative of the water is being attracted to that positive, and they're able to kind of surround it and isolate it, preventing it from easily bonding back in that ionic bond to the bromine or the bromide. Br minus is floating around there. The same thing happens there, but now we have the hydrogen side of things floating towards it. And bromide is pretty happy floating around in here. It's really electronegative, so it's got a pretty big, can spread that negative charge amongst a big area and have a lot of little oxygen or water molecules floating around it. Everything I'm drawing is obviously not to scale. But that's how these ionic compounds dissociate and are soluble in water. It's based on their electronegativity, their electron density, and how polar the object or the solvent is. So this is going to work well in here for water. But if we compare that to heptane, which is nonpolar, simply that reaction is not really going to happen. It's not going to be able to be surrounded by those ionic forces, so they're not going to have anything really separating it or stopping that potassium bromide from rebonding back together into a solid and basically sinking to the bottom of your jar. So you might be able to mix some of it in, stir it up real good, and get kind of a suspension, but it's slowly going to settle and fall back onto the bottom as a solid. Let's jump up to number 9. Number 9 says, explain why the ions of sodium and chloride are strongly solvated in water, but not in hexane, solvent composed of non-polar molecules. So this is very similar to what we were just talking about. Here, instead of potassium and bromide, we have sodium and chloride. And sodium chloride, it's really the same idea. You have a positively charged ion, you have a negatively charged ion, and we end up with water molecules surrounding it with their partial negatives closer to that positively charged ion. Those are each water molecules. Same idea with chloride. It gets surrounded, but now the partial positives, you get the idea, are getting closer to it. And that keeps them from being able to bond back to each other. Again, the hexane, which is just a 6 carbon chain, 1, 2, 3, 4, 5, 6. Yeah. That is, it's non-polar, so there's no dipole in there. So they're floating around in there, but we have this positively charged. Assuming that ionic bond breaks, we can have a heptane, which is just kind of floating in between them, but then it just kind of scurries past. It's not really attracted to them in any way, shape, or form, and then that bond can reattach again. And so that solid eventually does reform as those ions will hit again. So the only thing that'll break them apart is kind of energy being stirred into them or heated up or something to that effect. The ionic bond will kind of reform into a solid, and eventually it will just solidify and fall into the bottom. So now we get to the fun stuff when we start talking about molality. Number 38 here. We want to find the molality of these solutions. This is different than molarity. It's an easy thing to confuse. One, molarity has a big capital M, and that's equal to moles divided by the volume of the solution. But we were talking about molality. Molality has a lowercase m, not to be confused with that uppercase n, and that's equal to the moles divided by the kilograms of solvent. So that's an important thing to realize. It's the mass of the solvent in kilograms. Doesn't matter how much solute you have in there. We're only looking at the mass of the solvent, and the moles is the moles of solute. I should write. If I can spell solute, that'd be good. So the moles of the solute divided by the kilogram, or the mass of the solvent in kilograms. So these are two distinct things, and sometimes it's useful. A lot of times you use kind of the molarity and concentration when you're worried about how much of something's floating around in another thing. But a lot of times if you know how much the solvent you have, you can easier determine the moles of the solute using the molality of things. So here we want to calculate those molality. So in part A, on each of these really, they're giving us the mass of the solute. So we have 583 grams of this H2SO4. And they're telling us also that we have 1.5 kilograms of water. So we need to turn that grams into moles. To do that, we have to use the molar mass. Because anytime we have, say, mass divided by molar mass, that's going to equal, molar mass is in grams per mole, so we're going to end up with moles. So we need to find the molar mass of H2SO4. So we can do that by saying the molar mass is equal to 2 times 1.008 grams per mole plus, and we got to look this one up, I don't have sulfur memorized, 32.065 times 4, plus 4. So we're adding up the molar weight of each atom in here, and there's 4 oxygen atoms, 2 hydrogen atoms, and 1 sulfur. So when we add all these up, pull out my handy dandy calculator. 2 times 1.008 plus 32.065 plus 4 times 15.999. That's going to equal 98.077 grams per mole. Should put my units on here. There you go. So now that we have the molecular weight of that, we can take the mass of the H2SO4 that we have, divide that by the molar mass, and that'll give us the moles that we're looking for. So that's 583 grams divided by 98.077 grams per mole. 583 divided by my last answer is equal to 5.944. Say 5.94, and that's moles. So now we're ready. We can actually figure out the molality. Lowercase m is going to be equal to 5.94 mole divided by 1.5 kilograms. And our solvent, and water in this case, is given in kilograms, so we don't have to worry about converting it. If it's not given in kilograms, you want to make sure you convert your answer there. So this, if we divide by 1.5, we get 3.96 molal. And that molal is equal to moles per kilograms. Let's look at part B. So in part B, we're looking at 0.86 grams of NaCl, and we're looking at 1.00 times 10 to the second grams of H2O. So just like before, we need to find that molecular mass. So look at sodium, going back to our periodic table. Looking at sodium over here, that's 22.99. It's going to be 22.99 plus chloride, which is 35.453. See what that's equal to. It's going to be 58.443 grams per mole. So those are our molar mass of sodium chloride. We can then take the 0.86 grams, divide that by 58.443 grams per mole. See what that equals. That's going to be 0.0147 mole. So now we can look at our mass of water. So they said 1 times 10 to the second power. That's really just multiplying 1 times 10, which is 10, times another 10, which is 100. So this is equal to 100 grams of H2O. We're going to convert that to kilograms. Well, if I did that, I can say 100 grams times would be 1,000 grams per kilogram. That's my conversion. So it's really 100 divided by 1,000, which is this is equal to 0.100 kilograms. So I can then use these to find my molality. My molality is 0.0147 moles divided by 0.100 kilograms. And when you divide by 0.1, you're really just going to be multiplying by 10. So that's going to be 0.147 mole per kilogram. It's our molality. Looking at part C. Part C has 46.85 grams. And this is of codeine, which is C18H21N03. See if I can remember that. C18H21N03. All right. And they're giving us 125.5 grams of water. That's our solvent. Or of ethanol, even. So I should change that. I don't even think this was water. I think that was... No, it is water. Okay. Good. But this next one is ethanol. So we have to find the molecular weight of codeine, which is going to be equal to 18 times 12.011, the molar mass of carbon, plus 21 times 1.008, which is the molar mass of hydrogen, plus 14.011, I'm sorry, 007, which is the molar mass of nitrogen, plus 15.999, molar mass of oxygen. Ooh. So that's a lot there. Let's put it in our calculator. Make sure we do it right. 18 times 12.011 plus 21 times 1.008 plus 14.007. I missed the 0. Fix that. Plus 15.999. So that's going to be equal to 267.372 grams per mole. Okay, so now we have our molecular weight of the codeine. We have to find out the mass of it, or sorry, the moles of that. So we can take that 46.85 grams divided by 267.372. There it is. Something is off from what I had written down previously. Let me check that math real quick. Aha. I see what I did wrong. I forgot to multiply the oxygen by 3. So right here, 3 times, there we are. So that should really be 299.37 grams per mole. There we go. So that's a little bit better. Now we can cancel out, get our moles. That's 46.85 divided by this guy, which is going to be 0.1565. That's going to be in moles. So now they have the moles of things. Keep doing that. We need to divide those moles by the kilograms of our solvent. We have ethanol in grams. We need to convert that to kilograms. The easy way to do that is if you have grams to kilograms, just move that decimal place 3 places to the left. So this is going to be equal to 0.1255 kilograms. Same idea as just dividing by 1,000, which is what we did earlier. It's just a little bit quicker. 0.1565 moles divided by 0.1255 kilograms. It's going to be our molality. So I take this number here, and I'm going to divide that by 0.1255. That's going to be equal to, I'll move this over so I can fit her in. Be 1.25 equals 1.25. Say 1.247 is better. 4 sig figs. Thought it was 5 for a second, or 3. This is going to be mole per kilogram. So that's the molality of this one here. So it's a pretty straightforward process. Run it through one more time for part D. But basically, what we're looking to do is take whatever solute we have and turn it into moles, whatever solvent we have, turn it into kilograms, and you divide the moles by the solvent. The moles by the kilograms. So this last one is 25 grams of I2. And I2 is an easy one because it's just 2 times iodine, which is 126.90. is equal to 2 times 126.9044 even grams per mole. One 26.90 times 2. That's going to be equal to 253.81 grams per mole. And notice we only have 2 sig figs going on here. We can find out our moles by doing 25 grams divided by 253.81 gram per mole, which is going to be equal to 25 divided by that number, 0.098 moles. Yeah, again with that. So this was in 125 grams of ethanol. So that's pretty close to what we had before. We had 125.5. We can just go through that motion again. 125 gram of ethanol, which is just going to be equal to 0.125 kilograms. So now we have the moles per kilograms, or molality. It's going to be equal to 0.098 mole divided by 0.125 kilogram. So this number here is my moles. We're going to divide that by 0.125, which is equal to 0.7879. It'd be better. 2 sig figs. A molar. Molal. I always emphasize the ow. Molal. And that is going to be our answer for that one. It's moles per kilogram. Moving on. For number 44, we're going to assume this ideal solution behavior. So what we're looking at is the depression, or the increase in boiling point. So as you mix things into solution, you change the boiling point of the solvent slightly based on the concentration of that solution. And there's a basic equation that we use for these things for any ideal solution behavior, which is the change in the boiling temperature is equal to this constant of boiling. That's the boiling point elevation constant times the molality. So what this wants us to do is outline the steps necessary to solve the problem and then answer it. So first we're going to look at what is the problem. They want to know what is the boiling point of a solution. So they want to know kind of what that final boiling point is going to be if you mix in 9.04 grams of I2 into 75.5 grams of benzene. And we're assuming that I2 is non-volatile. So to solve this, we do a lot of the same things that we were doing before. But first, let's set up what we're looking for. We want to find what that boiling point is. So this delta T B is really equal to, call it temperature final minus temperature initial. And initial and final, initial is before you add the solvent or the solute to it, and final is after the solute. Okay, I could also say this is the temperature of benzene, capital B, and this is the temperature of the solution. Because we know the solution is going to be greater, or the boiling point of the solution is going to be greater than the boiling point of benzene itself, because it's not a pure substance. So this is going to be equal to that constant times the molality. So first we have to find what these values are going to be, and we're going to actually rearrange this now a little bit. So the temperature of the solution will be equal to that constant times the molality plus the temperature, the boiling temperature of benzene, which is my big capital B. So now we're solving for what we're looking for, that boiling point. So now we just have to make sure we have all those variables. For that KB, that constant, this is usually something that they look up on a table. So if you know the molality of something and you know the normal boiling point, you could determine that constant. So then we use that constant to determine molality or what the boiling point will be. So I have a little table here from the textbook. This is table 11.2 out of chapter 11. And we can see benzene down here. Oop, I should probably, let me just highlight. Ooh, yeah. There we go. And we can see its constant is 2.53. And its boiling point is 80.1, which is much less than water. I don't know why that's relevant, but it is. So that's at 2.53 for that. And the units for that is degrees Celsius per molal. And those are really just to make sure the units all match up. So we said that the boiling point, the temperature, capital B, of the boiling point of my benzene was 80.1 degrees C. So now that we have those, we just need to find what is the molality. Once we find that, we can plug them into there and solve for it. So that's kind of my step A, or part A. I'm outlining the steps necessary to answer this question. And really, it's defining the equation I need to use, rearranging that equation to solve for my unknown variable, and then find the known variables that I have, or solve for those if I need to. In this case, it's kind of a system because we need to solve for that molality based off of the mass of the solute and the mass of the solvent. But luckily, we just did a bunch of problems that does that, so we know how to do that. To do that, we first have to find out, well, what is the molecular weight of I2? Well, we just figured that out here. There it is. It's twice the molecular weight of I, or iodine. So that's 253.81. So I'm going to write that here. Molecular weight of I2 is equal to 253.81 grams per mole. So then we have to find out, well, how many moles of I2 do we have? So that's 9.04 grams of that divided by 253.81 grams per mole to get moles. 9.04 divided by 253.81 is equal to, this is 0.0356. Yeah. And this is going to be in moles. I think I'm right on the edge of my paper. So we'll go to the moles down there. So that's how many moles we have of I2. We then need to divide that by the mass of benzene in kilograms. So that's 0.0356 divided by 0.0755. Again, I moved that decimal place 3 places to the left. This is in kilograms. This is in moles. We have our molality. That's going to be equal to this value divided by 0.07555. Yeah. Which is equal to 0.472 molal. So I can now plug this in here, 0.472 molal. Now that I have that, I can solve for this guy. So the boiling point of our solution is then going to equal to 2.53 degrees C per molal times my molality, 0.472 molal, plus 80.1 degrees C. I like to always, once I get to this point, look at the dimensional analysis. Does this make sense? Molal cancels with molal. That leaves me with this degrees C plus degrees C. They have to be the same units to add them together, and they are, so I'm happy. So now I just have to plug it into my calculator. I do that because my calculator doesn't handle those units. So if I forgot to convert something, I'll catch it right there and I can convert it before I actually do any of the math. Times 0.472 plus 80.1. Make sure I put it in right, and we get this is equal to 81.3 degrees Celsius. And you see that's slightly higher than what we had before. So putting a little bit of I2 into the benzene increased the boiling point of the solution by, would it be 1.2 degrees Celsius. So that's both part A and part B of that problem. This one, we have a 12-gram sample of non-electrolytic is dissolved into 80.0 grams of water. The solution freezes at negative 194 degrees Celsius. Assuming ideal solution behavior, calculate the molar mass of the substance. I've got a little diagram here I pulled out of the textbook that kind of helps you visualize the steps and what we're supposed to do here. First, we look at the freezing point of that solution. Right, and here they're giving us solution freezes at that. We use that to determine what that delta T is. In this case, the solution is, the solvent is water. So water freezes at 0 degrees Celsius, so that delta T is going to be 1.94 degrees C. It's going to be depressed by 1.94 degrees Celsius. The molal concentration of the compound we need to figure out. And again, that uses that same equation, but now we're looking at the temperature of freezing. It's going to be equal to the constant for freezing times the molality. So we can utilize this once we know what this is, and if we know what Kf is, that constant of freezing, we need to look that up. We can use that to solve for this molality. So I just follow that idea. We can divide that constant of freezing to get molality. And just to make sure we know what we're doing before we move on, we're going to look over here. And there's our constant of freezing for water. The freezing point is 0 degrees Celsius at 1 atmosphere, and the constant of freezing is 1.86. So that's equal to 1.86 degrees Celsius per molal. So now that we have, and I'll just put my delta TF is equal to 1.94 here instead of having it over there. Now that we have those, we can solve for molal. Let's do that. So that's 1.94 degrees Celsius divided by 1.86 degrees Celsius per molal is equal to 1.94 divided by 1.86. That leaves us with 1.04 molal. So now that we have this 1.04 molal, for step 2, we need to find the moles of the compound in the sample. So how can we find the moles? So molal, this is really equal to 1.04 moles per kilogram. And that's the kilograms of the solvent itself. So we know there's 80.0 grams of water or solvent in here. So we can convert that to kilograms by moving that decimal place 3 to the left. That's 0.080 kilograms of water. And we can multiply. So if I take my 1.04 mole per kilogram and I multiply that by 0.080 kilograms, that's going to give me my moles. So multiplying this number times 0.080. So it's really 0.0834. To go 3 sig figs out. And that's going to be in moles. Now we have our moles of our sample. We need to determine now our molar mass of the compound. which is what this is asking us to do, calculate the molar mass of the substance. So now that we have moles, we can then just use the amount that they had. The sample that they gave us to begin with was 12.0 grams. So since molar mass is a grams per mole situation, we can just take 12.0 grams, divide by 0.0834 mole. I'm just going to bring this number. I hate rounding errors, so I always grab the last number out of my calculator. This is equal to 143.8. And we're going to go 3 sig figs, looks like. So 144 even. Grams per mole. So that sample could be a lot of different things. It could be combinations of different molecules, different atoms into a molecule, or just some elemental molecule. Either way, now that we know its mass, we can then narrow down the possibilities of what it could be. And I'm not going to go down that rabbit hole because it's a pretty big rabbit hole at this point. The bigger the molecular weight, the bigger that rabbit hole becomes. There we are. So this next one, in a significant experiment performed many years ago, 5.6977 grams of cadmium iodide in 44.69 grams of water raised to boiling point by 0.181 degrees Celsius. And they said, what does this suggest about the nature of the solution cadmium iodine? And this says CdI2, just to give us a hint on what that molecular formula should be. We should be able to determine that, though, based on this name. So if I hop back over to my periodic table, and we think about what are the common ionizations of cadmium, hey, there's a +2, really small on this one right here. So that's the main ionization state. I can also jump over to this guy here. You see cadmium is +2, iodine is -1. So that means it has to be CdI2. Anyways, so we can then use that to determine its molecular weight. Since they're giving us the mass of it, we can use that molecular weight to turn that into moles and go from there. So we're going to use the same formulas we've been using. This delta T of boiling, use a little b, is going to be equal to the constant at boiling times the molal. And we know that that constant at boiling is equal to, so we can go back to this table that's found in your textbook, table 11.2, and we want to look for benzene. We said that was 2.5. No, I'm looking for the solvent one. I'm sorry, which is water. And we know 100 degrees Celsius and 0.512 is the KB. Mm-hmm. 0.512. Don't know why I'm drawing in purple. I want to draw in green. Boom. Degrees C per molal is the units there. My temperature, I'll say temperature boiling of water, is going to equal 100 degrees C. And we don't really need to know that because they're telling us delta T of boiling is equal to 0.181 degrees C by experimentation. So what we need to do is find out what that molality is. So we can do that again by taking this cadmium iodine. So cadmium has a molecular weight of 112.441. So that's 112.441 grams per mole. Plus 2 times iodine. Iodine is 126.9044. 126.9044. And all of that is in grams per mole. So that we can use that to find our molecular weight. That's 112.441 plus 2 times 126.9044 is equal to 366.25 grams per mole. So we can use that molecular weight now to determine how many moles we had. So we had 5.6977 grams. Divide that by 366.25 gram per mole, which is equal to, that's 5.677 divided by that last calculation, brings us to 0.0155 mole. I left out a 9. Whoopsie. Insert a 9. So it changes just slightly to a 6. Just bring it out to 4 decimal places. This is actually to 5, but this one here is to 4. So I'm kind of rounding my intermediate answers to 4, although I still do my calculations with my full answer. So that now that we have how many moles we have, we need to determine our mass of solvent in kilograms. So that's going to be 0.04469 kilograms. Moving that decimal place over 3, adding in that leading 0. So we can utilize that, move that down just a tad into 0.01556 moles above that to find our molal. So this number divided by 0.04469 is equal to 0.0348 and 1. I need 4 sig figs. Molal. Straighten this out. Boom. So now that we have our molality, because we know what this is, 0.03481, we can now plug this into our equation to find out what the delta T should be if it was an ideal solution. So that should be equal to 0.512 degrees C per molal times our molality, 0.03481 molal. We can see the units cancel out, and we should get a temperature in Celsius, which is perfect. That's what we're looking for. It's really a change in temperature. So grab this number here. That's our molality. We want to multiply that by that constant 0.512. That's going to be equal to 0.178 degrees Celsius. So they claimed, based on experimentation, that they raised the boiling point to 0.8 or 181 degrees Celsius. That's larger, just slightly, than what we're getting in an ideal situation, which means that this solution is not what we would consider an ideal behavior for a solution. Most likely, it's a volatile or something to that effect. But we can tell that this is not ideal because the ideal solution should only have a temperature change of 0.178, where this actually rose up a little bit. For number 60, we're going to do the osmotic pressure of a solution containing 7.0 grams of insulin per liter. And they know the osmotic pressure is 23 torr at room temperature, 25 degrees C. Assuming an ideal solution behavior, what is the molar mass of the insulin? So this uses this osmotic pressure equation, which is osmotic pressure is this capital pi that we use. It's equal to the molarity times our gas constant times T. T being the temperature of that. So to remind you, the gas constant is equal to 0.08206, and the units for that is liters times atmosphere per mole Kelvin. And we know that our mass per liter, right? So what they're telling us there of this insulin is equal to 7.0 grams. So we need to we need to get everything into this point here where we can get the osmotic pressure. They're also telling us what that is equal to 23 torr. And we know a temperature is equal to 25 degrees Celsius. So to do this equation up here, we need to make sure we have everything in the right units for this gas constant here. So notice the gas constant is in liters times atmospheres per mole per Kelvin. Well, I don't have atmospheres, I have torr. I don't have Kelvin, I have Celsius is the idea. And I don't have mole, I have mass per liter. So there's a lot of conversion that is going to have to take place here. So let's start with the mass per liter. This idea of mass per liter, well, if I took and divided this by our molecular weight, okay, which is really grams per mole. So let me just change mass to grams and say this is grams per mole. Notice that my grams are going to cancel out. This is going to equal mole per liter. And mole per liter, that's equal to molarity. So I can take this 7.0 grams per liter and divide that by its molecular weight of the insulin to find that. And that's what we need to find, though. So I'm just going to write that in as a funky little m there. So I can say that 7.0 grams per liter divided by my molar mass is going to equal molarity. And that'll put things in the right ballpark of units too, because that's going to equal moles per liter. Now we can cancel out our moles and our liters when we multiply, leaving us with atmospheres per Kelvin. So looking at my atmospheres, I have 23 torr. So we need to convert that. So to convert that, the basic conversion ratio is 1 atmosphere divided by 760 torr. And there's a lot of conversion tables you can look up there. Simple Google search will tell you that as well. And we went over it a couple classes ago, a couple weeks ago, maybe a week ago as well. So we can do that conversion to find that. We can see real quickly that 23 divided by 760 is equal to 0.0303 atmosphere. And to convert from Celsius to Kelvin, all we have to do is take that Celsius temperature, we add 273.15 to it. Get rid of that. This is going to equal 298.15 Kelvin. Because Kelvin scale is on the same interval scale as Celsius, it just has that absolute zero that we count up from, which is a negative 273.15 Kelvin, or negative 273.15 Celsius is what I should have said. So now we have temperature in Kelvin and we have osmotic pressure in atmospheres. Now it's just plugging everything in. But we want to rearrange things a little bit. So I'm going to rewrite this equation where the osmotic pressure is equal to, instead of molarity, I'm going to go ahead and plug in this idea of my mass per liter divided by my molar mass. So that's equal to molarity. I'm going to multiply that, I guess, by an R constant and T. And now I can rearrange this equation to solve for my molar mass. The simple way is to switch that osmotic pressure and molar mass by multiplying each side by the molar mass divided by osmotic pressure. that will cancel out those guys and essentially switch. So I can solve for the mass per liter divided by, well, divided by nothing, times RT over the osmotic pressure. So now we have an expression we can use where it's just plug and play. We have all these values. The mass per liter is here, 7 grams per liter. We have our R value. We have a value in atmospheres. We have a value in temperature Kelvin. We're good. So that's just going to be, switch over to red, 7.0 grams per liter times 0.08206 liters times atmosphere per mole Kelvin. We're going to multiply that times 298.15 Kelvin, and then divide basically the lot by 0.0303 atmosphere. Doing our dimensional analysis, we can see that liters will cancel out with liters, atmospheres will cancel out with atmospheres, Kelvin will cancel out with Kelvin, and we're left with grams per mole, because the grams and the moles are the only thing left. So now that we have the right units for molar mass, we can then just do the math. 7.0 times, oops, that's a plus, times 0.08206 times 298.15 divided by point. This is one I want to grab from here. I should put parentheses around that. There we go. So this is going to equal 5,659 grams per mole. So that's a pretty big molecular mass. I was kind of skeptical about that myself. So I actually looked it up on the internet. Internet claims it's a little bit different than what I have there, but I'm still within less than 0.5% of what it is. It's just such a big number. I'm off by about, I don't know, 80 grams per mole or so. Assuming I did that right, 7.08206. Yeah. 98.15. Yeah. So yeah, I'm off by just a little bit there, but that's still really close, and we're in the right ballpark. And also, we should look at significant figures. Should be going to 2 sig figs based on that tour there. So 2 sig figs still rounds me round up to 57 grams, 5,700 grams per mole, which is spot on when you round and convert to the nearest 2 sig figs. So that's all I have for you today. Best of luck on everything, and I'll see you again Wednesday. If you have any questions, I'll be in the drop-in tutoring here in the Pingy app, so drop in there or check out and schedule an appointment with our chemistry tutor, Amir, and he'll be happy to help you out as well. Best of luck to you, and enjoy chemistry.